It's nice to be here. Since I'm the only author, so I don't have an excuse like Alice had that I have to be here so to give the talk. And it's something very simple and developed based on previous outstanding work. And consistent weighted sampling is just another example of a hashing algorithm for large scale search and learning. And so what we can hope for to accomplish with the hashing is that we hope to build, for example, linear classifier to approximate various linear or nonlinear kernels. The second task is to searching for near neighbors in sublinear time in some kernel space, approximately at least. So here's some examples we do for nonlinear kernels. We have resemblance kernels, which we can use BBMU as a hashing, and chi-square kernels. We can use the sign Cauchy random projections. And there's something called core kernels, which we can use permutation plus random projections. Core, if you're familiar with Rutgers, so core is a building for DMX, so happen to work out very well. So, and also random projections and the related methods for linear kernels are well known. So, so what is a mean? This talk is about min-max kernels. So what is min-max kernel? So suppose we have two high-dimensional non-negative vectors u and v. So we take the element-wise minimal, sum them up, and divide by the sum of the element-wise maximum. So that would be it's a number, nice number, ranging from 0 to 1. So it's a nice kernel to use. So this is the marvelous methods happen. I didn't do it, and so Mark Manassi is the one who did a lot of work, and somehow he never managed to get the paper published. And then someone else, Sergey, also published this version. So this is the version of the hashing method. So I say it's amazing because it's even hard to, when I look at it, it's amazing, right? So basically, you have a data vector u, which ranges from I to d. I mean, the index range from I to d, and we generate the gamma r, generate another gamma c, generate a beta. Then we do this operation, we get a t. So for every index I, so this is the t. So u is the data, r and beta are the random numbers. So t is an integer, and it's theoretically is unbounded. It could be negatively infinity or positive infinity. So it's an unbounded number. Then it go through this thing again, get a y and a. So eventually, what we need is find the location where the minimum a happens. So that's the I. So I star also ranges from 1 to d. So it looks like it's a finite number. And the t star is just the value at this I star. So, yeah. So when I look at this, I always feel if there's a Nobel Prize for hashing, this should deserve it. So the interesting probability results is that suppose for vector u, you get two numbers I and a t. There's another vector v. So v is different data vector. You do the same thing for using the same random numbers. We get two sets of numbers I and t. The probability that both I and t are equal is exactly the min-max kernel. So this is cool because this basically says, well, it shows that we can build a linear classifier, except the dimensionality is in the infinite space because the t is unbounded. But in conceptually, now we have a linear algorithm for computing those kernels. So this is cool, except this t is unbounded, and it would be nice if we don't have to have it. So it turns out it is indeed true, except the strict proof is hard. We have some proof, but it's not good enough to be presented. And we show that you only need I, you don't need a t. So here is so basically the information of t is very important, but it's already somehow encoded in I. It's not like t is not important, it's important, but it's encoded here. So basically, if I is equal, then most likely t is also equal. So there's no point to keep t. So So now we do not have to worry about how many bits should we allocate for t. So just save lots of hassle. Again, there's no strict proof, but we have an empirical proof. And so for this paper, the summary of the contributions are, so we need to study, first of all, you want to publish a paper like this, you have this convinced review of why do we care about min-max kernels. So we did a very extensive empirical study to show that min-max kernel works a lot better than linear kernels and also intersection kernels. And then we need to do a very intensive empirical study to verify this results. Then finally, we need to use this results to build larger scale linear classifiers, and the results approaching the results of kernel classifiers. So there are three things I have to do. And so let's see, what's the first thing? The first thing is show that min-max kernel. This is linear. This is SVM. So min-max kernel is the top curve. The linear kernel is here, and the intersection kernel is in between. So for those data sets, we can see that min-max kernel always work a lot better than linear kernels and intersection kernels. So this is how many data sets? So there's 15, and no, and there's another set of data sets. Yeah. So for some reason, I really like to do experiments. So yeah, I promise I try more, but I only present this many. Yeah. So we can see that a min-max kernel is an excellent kernel to use. Maybe in the future, people can talk about how to use that to replace RBF kernels. I think that can happen. Yeah. Okay. So this is the first thing. So the next thing is how do we show that this thing is true? How can you get rid of the t, and instead of just using I? So here, let's do experiments. So basically, this is from the text data. The text the A is just the number of the text A is a vector recording recording document IDs where the word A happens. So A and D, and so basically each word is one vector. And so F1, F2 is the number of non-zeros in that vector. And R is a resemblance. Says, well, suppose we do not worry about the number of occurrences. Just say what happened, you occur or not occur. That's a resemblance or Jacob distance. And then the MM is a min-max kernel. So we can see that the min-max kernel reduced to Jacob in the binary case. And we can also see that they're not the same. For real data, they're not the same. So so it's actually meaningful to study the min-max kernels because they're not the same. If you care about the difference, yeah, we can tell from these numbers. So now what we do is we use both methods, which we call zero-bit methods. This is zero-bit method to estimate this min-max kernel, or we can use the older bits methods, called full methods, to estimate this guy, and we can compute the mean square error, and as well as the theoretical values. The theoretical is easy because it's binomial, so we can see the mean square error is all, and the theoretical values, and using whether 0-bit or full scheme, they're about the same curve. So it's essentially always the same. So it's very, very boring, and so I didn't print all the plots. Yeah, but it's all boring because basically it already proved that it's empirically that it's good. But to show that, make it more interesting, so let's look at the bias. The bias is does show some difference. For example, in this curve, in the 10 to the minus 5 range, we can see that using 0-bit by discarding the t, we'll have some bias here, but that bias can be quickly fixed by using a little bit information of t. For example, if you care about that, just the first bit of t, then you can close the gap. Yeah. But that 10 to the minus 5, then in the mean square, you have to square it, then it vanishes. That, so you totally don't see it. So it's a very good heuristic at this point. Yeah. I say just for fun because mean square error tells everything. Yeah. I mean, tells most of things. Okay. So now we can build a classifier. So how do we do it again? So this part is nonlinear. This is a nonlinear kernel, and this part is actually a linear kernel because at least the estimator is a linear kernel. So we can use enough samples to approximate the probability, which in turn approximate the min-max kernel. So now this is the result. So basically, I have 4 columns. Let's look at the last column only. So basically, what happens is that I have 2 curves. The red curve is the using min-max kernel is a nonlinear. The blue curve is linear kernel, is of the regional data. The red curve is a nonlinear kernel of the regional data. And we can see that if we change the number of samples, for example, change it from like 32 samples to like 1,000, 4,000, then you will outperform linear kernel at some point, then you approaching the performance of nonlinear kernels. But all the curves the cost linear. And there's more data. And so what's the difference between this 4 columns? Well, basically, even this guy, I, is actually could be high dimensional. And when you implement, you want to implement with a small number of bits. So we can using 1 bit, 2 bit, 4 bit, and 8 bits. Yeah. So you always do this trick. Yeah. Okay. So that's the same curve. And yeah. So there's one thing I need to apologize is that to show this curve, especially if you want to show the red curve, I cannot do 2 big data sets, because what I do is I compute the kernel explicitly and dump in libsvm. And to do that, you will realize it needs a lot of memory. I have a machine with 1.5 terabytes of memory. I'm very proud of that because I spent a lot of money on it from a startup. But most people don't have that. So I don't use big data sets. But once we prove that this is seems to be true, so we don't if we don't care about this curve, if we don't care about the red curve, so we can use that for larger data sets, no problem. Except we cannot compute the original nonlinear curve. So this is web span data, and data has 350,000 examples. And the linear is 1 gram data. So linear SVM accuracy is more than 93%. So the original dimension is 255 of 250. Yeah, 255. It's 1 gram of letter gram. And so if you're using the proposed hash methods and 0-bit CWS with, for example, this is 8 bits, this is 1 bit. After 64 samples, you already approach the original linear accuracy. And with that, 64 versus 256, the range of dimension 256. And then with more samples, you got higher and higher. And we do not know what's the ultimate, what's the eventually can reach, because we cannot compute the red curve since we cannot compute the kernel explicitly. And yeah, so that's the that's the story. So there's 2 related issues. And when I show this to colleagues, and they say, well, what about random projections? So because the paper talk about the different routes instead of random projections. So I didn't talk about random projections, but the people ask us as well, the method of random projection of approximate linear kernels in a product, and we can see that linear, they don't often perform that well. They perform very well in certain cases, but in many cases actually they don't perform that well. That's why we care about deepness, those things, one of the reasons. And so for cosine, it often doesn't work well as nonlinear kernels. So that's one thing. So linear kernel doesn't work well as nonlinear kernels sometimes, often. And also the method itself, the random projection method itself, is typically not very good methods for approximating inner products. So that's one issue. The second issue is how does a min-max kernel compare to deep learning? So we have to confess that typically min-max kernel can approach the accuracy of deep learning, but cannot beat it. And perhaps surprisingly, there are also known cases that boosting a tree significantly outperform deep learning, and by a very large margin. So maybe one interesting future research is instead of worry about the deepness, let's say, well, can we design hashing algorithm to approach the performance of boosting? So talk about this. So there are 2 issues: the random projection and the deep learning. So what is a random projection? Random projection is basically you multiply the matrix with a random matrix R, you get a random matrix B. So if R is chosen random, for example, normal, then the inner product in A is preserved in B in the expectations. The variance, however, is very large. So there's in 2006 there's a paper called very sparse random projection. You can make it extremely sparse, and for example, you can make like 1 over 1,000. I mean, 1 over 1,000 entries are zeros, are non-zeros. Basically, if S is 1,000, there's 99.9% entries are 0. You make almost everything a 0, and you still get the same results as using dense projections. So this is 2006. However, the problem with the random projection is that you need lots of projections, and it's not accurate. The reason it's not accurate is, I just showed the results, is that, since this seems to be an important point, is that if you estimate the inner product A, suppose A is the inner product, and M1, M2 is the margins, so the error is actually dominated by the margins, not by the inner product. So that's a problem. That's why I typically need very large projections. So random projection, so this is the results in 2006, and this shows that the accuracy of random projections is typically very bad. And if you have better options, don't do it. But sometimes we do not have better options. We do random projections. Yeah. So moreover, in code 2006, we have the results for the inner product for the moment generating functions, which means that we can get the bounds, very accurate bounds for inner products as well. Yeah, in code 2006. Somehow those two papers are not known. So I'd like to use the opportunity to let people know, and also for people who care about the performance of our hashing with deep nets, we can see that so those are the data sets we use, and we can show that for deep net community shows that deep net beats SVM by big margin. However, in our 2010 paper, we show that trees beats deep nets by huge margin. Instead of 30% error, we get 10% errors. And there's the 10% happen at several stages. For example, is a MAR. This is a curve for MAR, which is a very popular industry algorithm. And this is a logic boost, which we use the 2010 version. And this is a ABC boost. So the performance is better and better, and compared to deep nets. So the hope is that maybe one day we can develop hashing methods to approaching this kind of accuracy. Right now, it's not possible. So I have to admit that. So summary is that the hashing is never the most optimal methods, but if you use it well, hashing is usually a very good method for lazy people, like engineers. So basically, if we work hard, so you don't have to. And so hashing usually does not outperform well-tuned deep nets. And combining deep nets and hashing is interesting research. And finally, so I want to mention one thing that for those who are curious, so I'm currently on leave at Baidu as a technical director working on many things, and CTR, and search and image search, and on data sets like 100 billion features and 100 billion, like 1,000 billion instances. Those are the routine things nowadays. And we do deep nets every day. So next time, hopefully, I'm allowed to say something about those applications. My guess is that I'm never allowed, but that's okay. And the important thing is that I don't say maybe that's against the rules. Yeah, so I don't. Yeah.
Thank you. Okay. So any questions?